Hello. So we continue from the last video. Uh, in the at the end of this slide in the last video, so the question is, what is the rule for specifying the normal form of an ordinary differential equation? So I have considered this. I have solved this example for you. So then you can think about what rule we have followed. Okay, let's look at the example 4. Linear and non-linear ordinary differential equations. Okay, the question is, specify the degree and linearity of the following ordinary differential equations. So we will be given some equations. So we have to tell about those equations, whether these are first degree or second degree. Okay, so this is the equation. So y minus x dx plus 4x dy. So what is the order of this equation? Yeah, let's make one correction that I think normally we don't use the word degree, we use the word order for the equation. So I think I should make some correction over here, but anyway, you understand that. Okay, so now we have this equation. So it is you can say that the highest order of the derivative is 1 in this case, and so it is a first order equation. And then the second thing is we need to consider is that whether that equation is a linear equation or not. So in this case we can see that this independent variable is y. Actually in this case there is something like a little bit tricky. So we will assume that y is a dependent variable and x will be a independent variable, because in this case differentials have been given. So if x is an independent variable, then derivative will be dy over dx. Okay, so in this case y is we assume that y is a dependent variable, So in this case, if y is a dependent variable, then we will see that y is linear in this case, and y is actually separate from dy in this case. Y is separate and y is linear. It means that it has a power of 1, so it is a linear function in this case. So this is a first order linear ordinary differential equation. Okay, the second one is here also. So in this case, y double prime minus 2y prime plus y is equal to 0. So in this case, we also assume that it is a dy over dx. So y is the dependent variable, and this in this case, these are the two derivatives, first and second derivatives, and y is a separate term from these derivatives, and y is itself a linear over here. So this equation will be also a linear equation, but this will be a second order linear equation. Okay, second order linear equation, linear ordinary differential equation. Now look at this equation. This equation is first of all, the order of this equation is 3, not because it is x is cubed over here. It's because it is the third derivative of y with respect to x. Okay, so it is the order of this equation is x. This is the highest derivative in this case, and whether this equation is a linear or not, so for this we need to look at the y terms, because y is a dependent variable in this case, and y term is over here, is separate from this dy and dx, and it is also a linear term. Okay, everything else is x, so we are not concerned with this in this case, x in this case. So y is linear over here, and it is separated from dy and dx. So in this case we will say that it is also a linear ordinary differential equation, but it will be a third order linear ordinary differential equation. So by considering these three examples, so just think about it and then try to infer some rule about how you identify a certain equation to be a linear, or in the other case non-linear, as we can see later now in the next slide. And the order of the order of the equation is also how you can determine the order of the equation. Okay. Next is specify the degree and linearity of the following ordinary differential equations. Okay, so now we will look at this equation. So order of this equation is 1 dy over dx. Okay, but whether this equation is a linear or not, this is a little bit tricky over here. In this case, if you see that if you separate out this 1 minus y term over here from this y, and then you will need to divide it by 1 minus y, 1 minus y, 1 minus y. Okay, here in this case we will get a term in which we will have the involvement of y divided by 1 minus y in this case. So since y divided by 1 minus y is not a linear term, so this equation will be considered as a non-linear. Okay, so first order non-linear ordinary differential equation. Let's see the next example. In the next example, you have y sine of y, and we all know that sine of y is not a linear term, so it is obviously a non-linear equation in terms of y. And remember that for the linearity, we are looking at the dependent variable. And previously, if you remember, when we wanted to determine whether that equation was an ordinary differential equation or a partial differential equations, we were only concerned with the independent variable. Okay, for the linearity dependent variable, we will look at the dependent variable. For the type of the ordinary or partial, we will look at the independent variables. Okay, so in this case, obviously this is a non-linear equation and with the second order non-linear. How about this? This is also obvious because it is y square. Y square is not a linear function. Okay, so that's it. So now what you can infer from this, from these examples, the rule, what rule you can infer. Okay, this is the question for you. Okay, let's do the example number 5. Okay, in example number 5, we are now going to verify the solution. Okay, so what do you mean by the solution? So by solution, we mean that the solution of the differential equation. Okay, so suppose we have been given this differential equation and we have been told that this is the solution. So we need to verify it. So that means this is the function. When we will input into this equation, then we'll satisfy this equation. So it's quite obvious. I mean, just like for the algebraic equations, so whatever the solution you find, you will input these values into that equation and then you can verify the equation. So same is the process over here. So in this case, how we are going to proceed. So I think what I will be doing, or what you will be also doing, you will agree with that. You will take a derivative of y, because this equation has a derivative of y over here. Okay, so I will take the derivative of y with respect to x. So this is just a fourth order polynomial, so its derivative will be obviously x power 4. So 4 will come here. Okay, so its power will be reduced by 1, so it will be 4x cubed. Okay, and then 1 by 16 is the coefficient which will remain, so it will be 1 by 4x cubed. I think you already know from your calculus 1 or calculus 2 courses how you take the derivative of the function. So it's the simplest of the derivative. So once you have done that, so you already know the value of dy over dx. Okay, so this means that you know the left hand side of this differential equation. So how about the right hand side? So So in the right hand side we have x and we have y, and y we already know is this. So what we can just do is that we can input the value of y in terms of this x into this equation and then see whether it is equal to 1 by 4x cubed. So let's go ahead and do that. So in this case, what you have done over here is that xy power 1 by 2, well, this is the same x over here, and then y power 1 by 2, y is equal to 1 by 16 x power 4. Where this has come from? This has come from here. Okay, the value of y is here, and then you have to take the square root of that. So just take the square root of that. So 1 by 4 x square. Okay, and then it is 1 by 4. If you simplify it, it will be 1 by 4 x cubed. So I think it's quite clear now. Both left hand side and right hand sides of this differential equations are equal to 1 by 4 x cubed. So which means that we have verified the solution. Okay, so with this, let's look at one more example. Yeah, this is a kind of like a more theoretical discussion, function versus the solution. Okay, so illustrate the difference between a function and the solution of the differential equation. Remember that basically the solution of the differential equation, as we have done in this example, is also a function, but there is slight difference between the meaning, and that meaning comes in terms of the interval of the function. Okay, so let's take the example. Okay, this example is if you take a function as y is equal to 1 over x, so this function we can plot for negative and positive values of y. So this is the plot for a positive values of x, this is the plot for the negative values of x. But there is one value which is x is equal to 0, where you get 1 over 0, okay, or negative 1 over 0. So at this value, this function is not defined. Okay, so if you take y is equal to 1 over x as a function, we will say that it is a function which is discontinuous at 0. Okay, so for all other values this function exists. Okay, but only at x is equal to 0 this function is does not exist. Okay, or it is undefined. Okay, so this is about the function. So now let's look at the solution. Okay, if for example y is equal to 1 over x is a solution for some equation, and in this case the equation is x y prime plus y is equal to 0, and we know that the solution of this equation is y is equal to 1 over x. Well, you can verify by your own. I have not done this verification over here, but I know that this is the solution. But when we say that it is a solution of this differential equation, we mean that it is a function defined on an interval I, which it is differentiable and satisfies the equation. Okay, so this is the difference between the solution and the function over here. So when we take y is equal to 1 over x only as a function, we will just say that it is it satisfies from minus infinity to plus infinity except 0. Okay, for the values of minus infinity, for the values of x from minus infinity to plus infinity except x is equal to 0. But when we say that it is the solution of the differential equation, we have to be very sure about the interval, and that interval is very important. Okay, for any value within that interval, that solution should hold true. Okay, so this is I'm going almost to the end of this lecture of this video clip, because the video clip limit is 15 minutes only. Okay, so in this case then that means that the difference between the solution and the function is that in the solution of the differential equation we have to be very much sure about the interval of the differential.